Okay. Okay, I'd like to explain one of the terms called specification error. Remember that we have the second step is called specified model, right? In specified model, we need to know the x variables, we need to know the functional form, and also the error terms. There are three components, okay? So a mistake in any of the three elements result in specification error. And I like to say something about the specification error is usually the most disastrous to the validity of estimated equation. So mean specification error is a very important topic. It's a serious mistakes. And we will explain this one in chapter 6 this semester. Okay? All right? And, okay, this is what I really wanted to mention, that regression gives the evidence, but does not prove economic causality. And also regression result does not prove the theory. Therefore, our goal should be specify only relevant explanatory variables, okay? And the selection of the closed complements or the substitutes is appropriate. But how far should you go? The choice must be based on a theoretical judgment, and such judgments are often quite subjective. So, in this point, in this course, regression analysis is not just only math, but also is an art. Is an art. Okay, so do not think in this subject is really just math oriented. It's more art in it. Okay, then anything else? All right, things we go through all this theoretical models and also theoretical thinkings. Do not always, if you have the result, is exactly the opposite way as the theoretical say. Okay, I'm not saying that you're not something like in innovators. Okay, do not thinking about yourself. It's really a very professional innovators. You know that theory is already for several years. I'm not just saying that they're all correct, but they're higher, the higher probability that is correct than what your result. Okay, therefore, maybe those prior study is not quite right, especially in this social science instead of physical science. For social science, it's hard. Sometimes the relationship is in both ways. Okay, so in either way, I mean the both way means they do have some literatures with positive relationship, and some theories postulate the negative relationship. So in both ways, you need to really support your theory, either in positive or in negative. Okay, and I think this is really art and also really important. Okay. So this is about these parts. Okay. Then anything else I'd like to mention it? Okay, step 3, hypothesize. Okay, hypothesize. So again, the expected sign of the slope coefficients, you have to hypothesize them before you collect any data. It's not the result of what you see. Okay? You need to hypothesize the expected signs of the slope coefficient before you collect any data. Okay? And if you have any doubts about the choice of expected signs, then you should document opposing theories and your reasons for it. Okay, always show the theory to support your result. Okay. Then what about collecting the data? Then I like to say that we have to spend some time in hypothesis testing, which is in chapter 5. Okay, especially those you didn't learn statistics undergraduate. Okay, the hypothesis testing is very important in empirical study. Okay, since we just use the data samples instead of the population. Okay, so hypothesis testing is the most important to do the research in regression analysis. So the step 4 is about collecting data. Remember this one. This step entails more than a mechanical recording the data, because the type and size of the sample size also must be chosen. So collect data is not just a very easy way. Actually, it's difficult. Okay, you need to really inspect and also clean the data. So this is also I want to explain it. Okay, the general rule regarding sample size is the more observations, the better. So it means as long as you can collect the data, the more the better. Okay, and those observations are from the same population instead of the different population. Okay, you need to collect the data from same populations. Okay, and ordinary researchers takes all the roughly comparable observations that are already available. Okay, as long as you can get those available data, just collect all of them. Okay, and why do we say the more the better? About this data, in regression analysis, all the variables must have the same number of observations. I mean, X and Y. I have X variables and Y variables, right? All of the X and Y variables should have same observation. What does that mean? That means there's no missing data in any variables without the complete same observation for all the variables. You are not able to run the regression, right? We should have Y and X. Okay? If you're missing one of the points in any of the X, if I have 3 X variables, and one of the X variables in some certain points is missing, the whole observations and whole elements cannot be used in the regression analysis. So usually those data, okay, have same frequency. What do we mean by same frequency? Either they are monthly data or quarterly data or annual data. Okay, I think this is especially for financial data. Usually we have this monthly, quarterly, or some variable like stock price. We even have daily data, okay? Often the frequency selected is determined by the availability. So some of the variables is provided in daily or weekly even. Daily, weekly, monthly, quarterly, annual. It depends on what they are available, what kind of frequencies they are available. Okay, and this is what I want to explain it to. Okay, the reason for as many observations as possible concern the statistical concept about degrees of freedom. I'd like to explain the meaning of the degrees of freedom. Degrees of freedom in statistics, okay, and it's the number of observations minus, since we're talking about the regression, so we're using the regression as an example. What do we mean by degrees of freedom? Means the number of observations minus the number of coefficients to be estimated. So if I have the regression like this one, I'm writing the regressions here. Oh, maybe this one. Y beta 0 plus beta 1, x1, but x2 plus beta 3, x3 plus epsilon. So this is the regression model. Okay. If I collect the sample n is equal to 100, I collect 100 observations. Means what? I have 100 y values, and x1, x2, and x3. And what do we mean by degrees of freedom? This is just sample size, right? This is called sample size. Okay, then degrees of freedom, I use DF, is what? It's using the number of observations, means the sample size here, 100. Then minus the number of coefficients to be estimated. So how many numbers I have to estimate it here? I'll estimate it this one, this one, this one, and this one, right? Right? So if I do the estimation, then it turns out with this one, then it can be like this one. So this depends on this, in order to have this. So what I really estimated is this 4 coefficients. Okay, so degrees of freedom is 100 minus 4. So my degrees of freedom turn out to be 96. This concept, you have to know that, okay? Then the reason for many observations means if I can collect 100%, 120, then my degrees of freedom becomes to 116. So it's 20 observation more, since I have the same number of estimates, right? So the more data, the more degrees of freedom. And what is this for? This is one thing I also want to. Okay.
What is a good degree of freedom?
Huh? What is
a good, sufficient degree of freedom?
Sufficient.
Yeah.
You mean sufficient? Usually, okay. If we talk about chapter 4, okay, it's like talking about the regression, theoretical, classical models. So in theory, there's a theory called central limit theorem. Central limit theorem tells us that the sample size, okay, must be at least 30. At least 30, in order to use the theoretical classical, probability distribution, which is 30. But usually, when you do your thesis, okay, especially for finance data, we usually say as many as possible. For 30, less than 100 is too
But I mean, like
Too little.
500 enough, 1,000 enough, 1,500 enough. Because it takes time to retrieve data, right? And we don't have a lot of money. We don't have like people doing it for us. So for the thesis, for instance, let's say we can have a sample size like a degree of freedom of 500. Does that sound
sounds reasonable.
reasonable? Yes.
Yeah, I think so. But it's also really depends on what kind of research I'm working with. If you're working with those surveys, okay, unless you are working on the computers, you don't have spend much money about it. If you do this survey questionnaire, it really spends a lot of time and also money, okay? And so in that case, you may thinking about or talk about with your advisors about the sample size, okay? But for financial data, do you know that we have all this data set in Zhongyuan universities? They do have this data set, and all this financial data you can just collect it from the data set. In that case, you don't need to spend any money from collecting the data. So in that case, you can do as many as possible. So usually, like more than 10,000 is possible, especially for listed company. I think working with Taiwan's company data for listed companies data for I think we have at least 1,800 companies. I mean, every year. So if you collect this like 10 years data, then it's more than, it's 18,000 for annually. I mean, annually. Then if you do the monthly or quarterly or even, triple or 4 times more than the data you have. Okay? So we will say that as many as possible. And thinking about why do we do as many as possible, I like to read this sentence. We're working with this statistical model. Usually it's not fixed. It's a random. Okay? So the more data, okay, the result is more close to the theory. Okay? For example, in theory, if I flip a coin, okay, what is the probability that I get head? 1 over, no, I mean the coin is 2 sides, so 50%, right? But now, if I do the experiment, if I do 10 times, okay, how many of the head are you able to get? It really depends on how you flip, the result of your flip, right? But if you do 100 times, or 1,000 times, or 10,000 times, the more you do, the more the probability is getting close to 50%, isn't it? Do you agree with that? The more chance I will get, the final result is approaching to 50% more if you do more times of flipping the coin. Okay, this is what I'm saying, that the more a coin is flipped, the more likely it is that the observed proportion of heads will reflect the true probability of 0.5. So with this reason, when the number of degrees of freedom is large, every positive arrow is likely to be balanced by a negative arrow. You see the saying? You see the expression like this one? And when degrees of freedom are low, the random elements is likely to fail to provide such offsetting observations. Okay? So this is the reason why we need more sample size. The more sample size, the higher the probability, the degrees of freedom is bigger, then it's more likely that the positive arrows is balanced with negative arrows. And it's more chance that will reflect these true probabilities. Okay? Does that make sense? Okay? Okay, last parts about the collect data and inspect. Okay, unit of measurement. For every variables, we do have the unit measurement. Same variables measured in different scales does not change the result of regression analysis, except in interpreting the scales of the coefficients. So remember, same variables, if you measured in different scales, this is what I'm saying, that in your second project, we're using centimeters for the height, right? And kilogram for the weight, okay? And you can use also the same measurement unit as our textbook using feet. The height is above 5 feet, right? So also the centimeter is above 150 centimeters. And weight, you can also use pounds. Do you know how to convert with a kilogram to pounds? Do you know how to do it? With your data, and use two different measurements. Okay, one pair is kilogram with centimeter. The other one is
11 pounds is 1 kilogram.
no. If I didn't, 1 kilogram equal to 2.2 pounds. Am I right? 1 kilogram equal to 2.2 pounds. Okay? And 1 foot equal to 30 centimeters. Okay, use this relationship to change your measurement units from the kilogram centimeters to pounds and inches. Okay, inches. Then I like to you to check the result of this one. This one say that same variable measured in different scales does not change the result of regression analysis, except in interpreting the scales of the coefficients. This is just the measurement units, right? So I like to do both, okay? Then you can see if I change the measurement, how does that change the coefficients. Okay, I think this is already done in chapter 1 and chapter 2, right? We already explained that before in the class.
So we do it for the assignment as well.
Yes, for this assignment. Okay, for this is assignment, everything is the same. You just have to run twice of the same regression. All the results will be the same. Okay? All right, so this is really ask you to taste what does this wording means. So this is all saying that all conclusions about science, significance, and economic theory are independent of units of measurement. In other words, the unit of measurement will not change the science, will not change the significance about the relationship between X and Y. Okay? Although, the significance, we haven't learned it. This in chapter 5 for hypothesis testing. Okay, but we just have to see the sign first. So far, we didn't really talk about the significance yet. Okay, anything else? Okay, here, how do you inspect your data? You can obtain a plot of the data and look for the outliers. Does anybody know outliers? Outliers means extreme values which away from the rest of the data. Okay, and especially if you look at a plot, it's easy to identify the outliers. Okay, so look at the plot and look at the mean, maximum, minimum, each variables. Are any observation impossible or unrealistic? Okay, after you have the data, you check the summary statistics. I think this is one of the steps in our assignment, second assignment. Okay, we have to follow the step. So step 4 is step 2. Calculate the summary statistic. Do you know how to do it from eViews? There's a function, you can choose it for summary statistics. You know how to do it? Or maybe you can discuss, within the group. Okay, if you don't know how to do it, So this is what we say. From summary statistic, you can see the mean, maximum, minimum of each variables, and to see is any outliers too. All right. How do we clean the data? So this is what we say. Okay, be careful. Okay, any observations can be dropped from a sample, but an observation can be dropped from the sample, but only if the correct number cannot be found, or if that particular observation clearly isn't from the same population as the rest of the sample. Sometimes it's hard to find it out, right? And second one, the mere existence of an outlier is not justification for dropping that observations in a sample, and not just a well-behaved ones. That means that if we look at all this data, all these well-behaved ones, or any outliers, you may not easily drop any of them. It's easy to accept well-behaved data. When we say well-behaved data, means that it's not an outliers. Okay, it's easy to accept the well-behaved data. And it's easy to drop the outliers, things, maybe that's incorrect numbers or something else. But this one saying that unless you can really check that observation is incorrect, you cannot just drop it off. Okay? This one just help you to identify the unusual observations. And it doesn't mean that you can drop it off. Okay? Then, I really want to mention that from step 1 to step 4. So this is kind of warning, okay? Believe it or not, it can take months to complete from 1 to 4. I mean, this is about your thesis. It's not our assignments, okay? Believe it or not, it can take months to complete step 1 to step 4 for regression equation. But computer programs, so far we're using eViews. Okay, there's something else, don't you have to know, okay? We're using eViews, okay? But a computer program like eViews can estimate that equation in less than a second. I mean, you spend a lot of time from step 1 to step 4, and after you put all this data into the eViews, within a second, all the results come out. So this one is really difficult, important, tedious, time-consuming, but it's worthy, it pays to do it. Okay? All right. Let me see. Anything else? Let's see. Okay. Number 5. So far, we're working with OLS because we just learned OLS. So this is saying that if in the future, if you have another estimation technique is used other than OLS, and the reasons for that alternative technique should be carefully explained and evaluated. So if you don't use OLS methods, you're using other ways, you need to carefully explain why do you need to use the other estimates. Okay, then you have to evaluate. And beginning researchers should be prepared to spend a considerable amount of time doing evaluation. Just check the result, check the result. Okay, and okay, you need to evaluate your result in a variety of ways. Okay, for example, how well does the equation fit the data? Do we learn this one? How well did the equation fit the data? We just explained in chapter 2 using the R-square or adjusted R-square, right? But that is not only one measurement, but this is only one we learned so far. Second, were the size and magnitude of the estimated coefficient what you expected? We again and again, we are talking about the signs of the coefficients, right? What else? Making the choices is one of the artistic elements of applied econometrics. It's often worthwhile to estimate additional specification of an equation in order to see how stable you are. Okay, this is we will talk about in chapter 6. about the sensitivity analysis means that we are allowable to use some other appropriate estimation or additional specification. When we say the additional specification means what? Different x variables or functional forms. Okay, different functional forms. So if we have the chance to do like that, then in that case, we can check how stable our observed result. Okay? All right? Okay, documents the result. It means how to express, how to show your result. Although, I know the thesis, we also have to follow university's format to document your result. Okay? We will talk about how to document those equations. So the estimated standard error of the estimated coefficient that we will talk about in chapter 4.2, and also the t values. All this is in chapter 5, hypothesis testing. So we'll get to that when I talk about chapter 4 and chapter 5, and they'll show you how to show your result. Okay, all this written documentation must contain enough information so that the entire study could be replicated by others. This one is important. Okay, your thesis can be replicated by others in order to check the correctness. Nowadays, I don't know whether those foreign students, you may not know there's some situation in Taiwan, especially when at the end of the year we have the important elections. Nowadays the candidates are question, their master thesis or PhD dissertations, because they find out that their study is copy, is plagiarism. Okay, they plagiarized from other peoples. Okay, so the document's result is very important, that it can be replicated by others. So you have to say explanation for the models and your assumptions, also the procedures and data used. Okay, definition of the variables and so on and so forth. Okay, and if there's a series of estimation equations, the several equations, then the table should be provided the relevant information for each equation. In other words, also you have to provide your data in order to other researchers to do the duplicate, to do the replicate, in order to check the correctness. Okay. They say that if the data are not available generally or available only after computations, the data set itself might be included in the appendix. Okay, I think this is very official. It's not like our assignments. We already have the same data set. Everybody do the same data set, so itself you can check whether you have the correct result or not.
Maybe I already asked you, but if you have to take like
Excuse me.
several thousands of samples of data,
Yeah.
I might already have asked you about this, but I forgot. So, if we have to use several thousand of sample of data, right? How should we normalize it so that it can, for instance, be imputed in eViews?
You mean normalize?
Yeah, standardize, like
Standardize the variables or what?
no, the data samples. We should use what, like learn Python or something? Because we might not be able to retrieve the data in an already normalized and computable, structure. So we have to
Well,
make it so.
You know, most of the time, I'm thinking, most of the time, unless it is already available, okay, like stock price, you cannot change the stock price. Yeah, but if you have some variables, okay, which have some definitions, usually is you have to correct the related variables first and do the computations in order to get the final definition of the variables you wanted. And all of them, you just have to, if you have the data set, especially for finance data, okay, you can get it from the data set, then download first all the related related variables for your own variables. Then do the computations. Then after the final definition is as the observation of your variables, which you wanted.
Well, that wasn't really the question, but it's okay.
Okay.
I'll find a way.
Well, maybe there's some other, tools. You can use it. I don't know. Okay, because I don't know what kind of studies you wanted to do, and any spatial tools which you can always available.
I think, can I say something?
Yeah.
Sure.
Use this one.
I think you are asking about how to normalize your data, right?
Yeah.
Using eViews or other softwares. Is that your question?
The question is that,
Because-
Why do you?
what are the different tools
Yes.
are in our possession in order to normalize the data? We can't get already normalized.
Yes.
Well,
For
excuse
instance,
me.
like Professor
Yeah.
said, 1 minute. If you download the data from our school website, right, which is eView Pro, or what's the name again? TEJ Pro, they will give you the data in an Excel format, but that data is not clean, it's not normalized. So you have different ways to normalize the data. If eViews, you have to do it and redo it again because you don't have commands. But if Stata or R, you can easily save it as a CEV or Excel file, then you use R with your own commands. R will give you commands on how to normalize that data. Then you normalize the data first. But before you do that, what Professor said is your variables should be clearly specified. For instance, if you want to check on sales, they will give you sales. But let's say, for instance, you want to check on profit performance. There are different things that you need to subtract from sales. You need to do that in your own Excel by yourself. Then later you have your data structure. Then you use the command in R to normalize it before you run your regression.
The command for normalizing data, you input it directly in Excel.
Yeah, it's just a code. No, you don't put it in Excel. You put it in R or Python. But for eViews, as SPSS, they are input outputs. It means you have to clean it first by yourself using Excel. Then you input. It will only give you the result. eViews and SPSS cannot do data normalizations because they ask you to give them, they give you.
So the answer is to use like
Python, R, or other statistical tools to normalize your data.
Yeah. Okay. Yeah. And why do you mean normalize your data?
It means that big data sample to be easily analyzed by an algorithm, it has to be presented in the exact same way.
Yeah.
Because if there is some slight difference, the algorithm just will say, oh, not a problem.
Yeah, yeah,
So you have to normalize it. That's why we call it.
yeah.
So arrange it in the same order.
Yeah, okay. And sometimes Excels can, I mean, all these positions,
But it's very tedious.
it's very tedious. Yeah, okay. So if you can use the Python or any other tools, and I think is
R is better. R is built for statistics.
R is a programming language. Oh, okay.
It's way better.
yeah. I think R is also free.
Yeah.
The program is free.
But that's a programming language. It's always free.
Yeah.
The fact that you have to study, that's not free. I mean, it's free.
Oh yeah. I mean,
Maybe,
okay, sure. Nothing is free, right? Okay, all right. So this, I think I already done this part, and also the examples. Okay, let me see what I show the examples. Okay, you all remember that the y variables for our examples. The number of customer that. This is a really definition in our examples. How do they measure the sales? In your thinkings, how do you measure the sales? I think, first of all, I'm always thinking about the money, right? The money. But in this case, how do they measure the sales? The author tells us that they are measured by the number of checks or bills that the servers handed out. I mean the number of the bills or checks that the servers handed out. Instead of summing all the monies, okay, they are looking for the bills. The number of bills means that the more the bills, the higher, the more customer come in. So they are really emphasize the number of the customer. Okay, if more customer mean the more customer means the more possibilities to have high sales. So this is really different from what our thinking. Okay, they are not measured by the money itself, but measured by the number of checks and bills that server handed out, or waiter or waitress handed out in a given location. So they already, since there's a chain restaurant, so they already have some data from other 33 restaurants. Then using the 33 as an original data and set up a regression model and put all this data in and set up a regression. Okay, so this is the example. And later I'm going to show this result. Okay, and also I'm going to talk about the dummy variables, which is important. Okay, let's take a break.